child has been drinking from a juice box and decides to play a game. He blows bubbles into the juice box, pressurizing it to an absolute pressure of 120,000 pascals. To his surprise, when he takes the straw out of his mouth, the juice box squirts juice all over him. A. Calculate the velocity of the juice as it leaves the straw. B. If the radius of the straw is 1 millimeter, calculate the volume rate of flow. And C. Explain in 1 to 2 sentences why the juice box stops squirting before all the juice is expended. There are 3 notes that apply to this problem. We're to approximate atmospheric pressure as 100,000 pascals, and to use the density of the juice to be 1,000 kilograms per cubic meter, and to approximate the velocity of the juice to be 0 while it's still in the box. This is a problem in fluid dynamics, and we analyze fluid dynamics by using the Bernoulli equation, also known as the Bernoulli Principle. The style by which we solve a Bernoulli problem is very similar to that of conservation of energy. We identify 2 locations within the same fluid and connect these 2 locations by the Bernoulli factor. The 2 locations that I will choose are the top of the fluid itself, location 1, where it is in contact with the pressurized air at 120,000 pascals. And for location 2, I'll choose the exit point of the juice from the straw. The Bernoulli principle tells us that the quantity pressure plus 1/2 density times velocity squared plus density times g times the height is the same value at all locations throughout the fluid. The manner in which we realize such an equation is we select each of our 2 locations, beginning with location 1, having pressure 1, velocity 1, and y1, and set this equal to the sum of the same 3 quantities at location 2. We've been told that the absolute pressure inside the juice box is 120,000 pascals, and that we should consider the velocity term to be negligible. Whether we have a rho gy term all depends upon where we decide to set y equals 0 in this problem. Just as in energy problems, it's customary to set the y equals 0 location at the lowest point being considered, and in our case, that's location 1, so we'll have a 0 for our potential energy term at location 1. At location 2, the juice touches the air. Any 2 fluids in contact with one another have the same pressure, and so the pressure of the juice at location 2 is 1 atmosphere, which we're approximating as 100,000 pascals. At location 2, the juice certainly has a velocity as it squirts all over the child. And at location 2, we are no longer at the y equals 0 point, so that there will be a potential energy term of density times g times the height of 0.08 meters. The only unknown at this location is the velocity v2, and so we can solve for this quantity, yielding a velocity of 6.20 meter per second. In part B of this problem, we're asked to quantify the rate at which the juice leaves the juice box. There are 2 common ways to do this. The first is to calculate the density of the fluid times the area of the exit point times the velocity with which the fluid leaves. Checking out the units on this quantity, we recognize that this tells us the number of kilograms per second that exit the tube. That's not what we're asked for. We're asked for cubic meter per second. And the simpler quantity, area times velocity, yields cubic meter per second and tells us the rate at which the fluid is flowing out of the straw. Since the straw is a circle of radius 1 millimeter, its area will be pi times the radius squared. That multiplied by the velocity of 6.2 meter per second yields a volume rate of flow equal to 1.95 times 10 to the minus 5 cubic meter per second. Finally, we've been asked to explain in 1 or 2 sentences why the juice box stops squirting before all the juice is expended. The answer to this question is found in the figure. As the juice drains through the straw, the level of the juice will continually go down. As a result of this, the gravitational potential energy term will become larger, but more importantly, the volume of the gas that has pressurized the juice box and is causing the flow increases, causing the gas pressure to decrease, and these two factors combine to the point that eventually the juice stops flowing long before the juice has been expended from the box.